Okay, so hi everybody. It's my pleasure to introduce John. Um, John is a postdoc at UC Davis. He received his PhD from the University of Washington in 2016, where he worked with Jeff Williams and Bill Noble. John develops faster and more efficient machine learning solutions for massive scale problems, particularly those in computational biology. So John focuses on both optimization for high performance computer architectures, particularly for GPUs, and convergence analysis for generative and discriminative training of graphical models. So he's a recipient of the UC Davis Award for Excellence in Postdoctoral Research and the UW Genome Training Grant. Okay, John, so perhaps you can pronounce correctly your family name or last name.
Oh, my last name, Halloran?
Yes. Okay, perfect. Thank you.
Yeah, no problem.
The stage is yours.
Okay, thank you. Well, thanks for hosting me, Halloran, and thanks for everyone for having me. Today I'll be discussing my work, accelerating machine learning for computational proteomics. So this is joint work with David Roth, who's my PI over at UC Davis, Bill Noble, who is my PhD advisor over at UW, Lucas Gale in Stockholm, and Chezang Havanzur. So in today's talk, we'll begin by discussing how protein subsequences, which are called peptides, are typically identified in practice. We'll then look at how graphical models may be used for accurate peptide identification. And finally, we'll look at how SVMs are used to further improve identification accuracy. Now, these two methods will allow us to look at two different approaches to accelerate machine learning systems. For graphical models, we'll theoretically characterize when the log likelihood is convex, leading to fast and efficient conditional maximum likelihood estimation. And for support vector machines, we'll leverage high performance compute architectures, and in particular, GPUs for ultra-fast large-scale learning. So the pace of the talk will be a little quick, but I'll keep my eyes on the Q&A if anyone has questions throughout. So let's get started. So assume that you're given a complex biological sample, such as a drop of blood. Now you'd like to know what proteins are present for this particular complex sample. The most widely used technology to do this is tandem mass spectrometry, which is typically abbreviated as MSMS, and which I'll call mass spec for short. A typical mass spec experiment is as follows. So we begin with our complex sample, which is comprised of proteins. Now, proteins can be quite long and difficult to analyze. So we cleave these proteins into shorter subsequences called peptides. Each peptide then undergoes 2 rounds of mass spectrometry so that at the output of this entire process, we obtain a massive collection of spectra. Now, each spectrum in our collection is representative of a peptide from the original complex sample. So the following is an example such observed spectrum. The x-axis measures the mass to charge, which is typically abbreviated as M to Z, and the y-axis measures the intensity at each M to Z value. So the problem that we're interested in then is for each observed spectrum in our collection to identify which peptide was responsible for generating it. The most accurate solutions to this problem utilize a database of peptides as follows. So assume that we're given the observed spectrum on the left and database of peptides in the middle. We compare the observed spectrum to a peptide using a scoring algorithm to produce a score. Now, the triple consisting of an observed spectrum, peptide, and score are typically referred to as a peptide spectrum match, or PSM for short. Continuing in this manner, we score other peptides in the database. We then rank these peptides based on score and output the top ranking such PSM. Now, we did this to identify a single observed spectrum. We repeat this process to obtain a list of top PSMs, one for each observed spectrum in our entire collection. So the most difficult aspect of this entire process is designing an accurate scoring algorithm. So all scoring algorithms make use of features based on the peptide called B and Y ions, where B ions correspond to prefix masses of the peptide and Y ions correspond to suffix masses. So for example, assume that we're given the following charge 2 peptide string. We would expect to see the B ion corresponding to the prefix mass highlighted in blue and the corresponding Y ion corresponding to the suffix mass highlighted in red. So the numbers in the B and Y ions denote the length of the substring considered. We would also expect to see a B ion B2 and corresponding Y ion Y2, and so on. So if we look back at our earlier observed spectrum example, the following illustrates the B and Y ions of the generating peptide. So B ions are plotted in blue, Y ions are plotted in red, and spurious noise peaks, which we're calling insertions here, are plotted in gray. So some things to note are that there are many noise peaks in these observed spectra, so they're extremely noisy, and not every B and Y ion appears in the observed spectrum. So for instance, B1 and B2 are missing, and Y6 and Y7. So these two types of phenomena, a large number of noise peaks and a large number of missing B and Y ions, tend to make these observed spectra extremely difficult to analyze in practice. So in order to actually generate PSM scores, all scoring algorithms gather all of these B and Y ions together into a single theoretical spectrum. They then compare the theoretical and quantized observed spectra to one another using a scoring function. Now, the specific form of the scoring function usually characterizes the scoring algorithm. So for instance, the very first scoring function ever is called X-score. It debuted all the way back in 1994. So if we let X be the theoretical spectrum and Z be a quantized version of the observed spectrum, then X-score consists of a dot product, that's the first term in X-score, minus a cross-correlation term. So X-score is usually viewed as a foreground score minus a background score. The foreground score measures how well the theoretical spectrum fits the observed spectrum, and the background score is meant to penalize how much shifter versions of the theoretical spectrum overfit to the observed spectrum. So X-score remains extremely popular and widespread use, despite being over 2 decades old. It's actually really difficult to get people to stop using X-score. So since 1994, when X-score was debuted, a long list of new scoring functions, far more complicated and accurate, have since debuted. The following is a short list of some of the most accurate. So these are indicative of the state of the art. At the very top, we have MSGF+, which is extremely accurate and it's very popular in the community. MSGF plus computes p-values for a very simple dot product score using dynamic programming. X-score p-values takes a similar approach as MSGF+. So it uses dynamic programming to compute p-values for X-score, which, as we saw, is a linear score. And finally, we have 2 of my methods. So we have DRIP and DIDEA, which are dynamic Bayesian networks, which model the generative process by which peptides produce observed spectra. So for the purposes of our talk, we'll actually be focusing specifically on DIDEA and some of my recent work on DIDEA in NeurIPS papers from 2017 and 2018. So some background, DIDEA was first introduced in 2012, and while it was shown to be pretty accurate, it's the training framework which it was first produced with, which was actually extremely ineffective. So it could only learn a single parameter. I used a heuristic grid search, which was extremely expensive. So we'll be working towards making its training framework more flexible, able to learn more parameters, as well as adding theoretical guarantees to it. So let's take a closer look at DIDEA. So DIDEA was actually developed as a probabilistic analog to X-score, packaged in a DBN. So the frames of the model correspond to the peptide sequence, so the sequence of peptide characters. So we'll take a closer look at the model. To look at it a little bit more in depth, we'll let X be an arbitrary length L peptide sequence, whose sequence of characters is X1 through XL. We'll let S be an arbitrary observed spectrum, and we'll let Z be a quantized version of S. So the following is the graph of the DIDEA model. It's depicted as a DBN template. So nodes and edges are collected together in time instances called frames. frames are indexed using the time variable t. So we can see that t runs from 0 to L, the length of the peptide. The first frame is called the prologue, and the last frame is called the epilogue. The frame in the middle is called the chunk, and given a new peptide sequence, the chunk dynamically expands to fill all middle frames between the prologue and the epilogue. So in all frames past the first, we have observed variables x, which correspond to the sequence of peptides. So if we consider traversing the model from left to right, we would actually consider the entire peptide sequence. Next, we have the b variables, which effectively accumulate mass, prefix masses in subsequent frames. So the b's actually correspond to the sequence of b ions for a given peptide, where the b ions are computed from left to right. So similarly, the y's correspond to the y ions, which are computed from right to left and correspond to suffix masses. The observed O variables are virtual evidence children, and they grant us access to the observed spectrum, where we use the B and Y ions as indices into the observed spectrum. And finally, the hidden variable tau acts to randomly shift the B and Y ion indices in each frame. So at a high level, you give this model a peptide string, and it very efficiently sequences through all pairs of B and Y ions, as well as all shifted pairs of the B and Y ions based on tau. So in order to score observed peaks, the emission functions of the model look like as follows. So the emission functions correspond to the conditional distributions over the O's. So just looking at the B ion emission function, we have the B ions shifted by tau, used to access the quantized version of the observed spectrum Z. And finally, they're passed into a possibly unnormalized distribution F to weight these peaks. And this unnormalized distribution is parameterized by theta, which is some parameter which we'd like to learn. So in order to actually assign PSM scores, sum product inference is computed in DIDEA to calculate the log posterior score, which is written here. So it's the log posterior of tau equal to 0, so the shift being equal to 0, given the peptide and observed spectrum. So the motivation behind this score can be seen if we just expand this a little bit. So we can see that there are two terms. One is the joint distribution evaluated at tau equal to 0, and a negative term, which is the log likelihood, where we marginalize over all of the shifts tau. So the prior on the taus is actually uniform, so this second term decomposes further, and it looks like the following. So this kind of looks like an equation which we've seen earlier in the talk. So basically, DIDEA's scoring function DIDEA's log posterior scoring function consists of a foreground score, which is meant to measure the similarity between the theoretical spectrum and the observed spectrum, minus a background score, which is meant to penalize overfitting of shifted versions of the theoretical spectrum. So when I mentioned that it was built as a probabilistic analog of X-score, this becomes immediately far more obvious when you look at its actual scoring function. And of course, as I previously mentioned, this specific quantity is computed very efficiently using sum product inference. So how does this model actually perform in practice? The following is a typical performance plot. So this is evaluating a worm data set. The x-axis measures the false discovery rate, or FDR, and the y-axis measures the number of spectra identified at each FDR. So higher up, higher curves equate to better performance. So we can already tease out some trends. So we can see that the two p-value methods, MSGF plus and X-bar p-values, so the pink curve and the yellow curve, are already far more accurate than the green curve, X-bar, which is what you would expect. Those are far more complicated models. And IDEA is actually more accurate than all of the methods, including our other DBN drip. So in practice, it works pretty well, with IDEA. But if we look at other data sets, so if we evaluate a yeast data set, then we can actually see that DIDEA underperforms. So MSGF plus in pink outperforms DIDEA at low FDR thresholds. At say an FDR of 1%, MSGF plus is identifying more spectra. So effectively, at very stringent FDR thresholds are what people care about very much in practice, especially at FDRs of 1%. So in recent work, we sought to find out why DIDEA was effectively underperforming. And what it turned out to be was what I mentioned earlier, is that its training framework was highly inefficient. So as I previously mentioned, when it was originally debuted, it could only learn a single parameter. To learn that single parameter required a very expensive grid search, which required evaluating an entire data set. And all of these training inefficiencies stem from the fact that the emission function used was extremely complicated. So I won't put it up, or I won't show it, but effectively, it did not allow any type of theoretical characterization or any type of global convergence analysis. So in our NURBS 2018 paper, we sought to rectify this equation. So we effectively looked for general classes of emission functions for Bayesian networks, which would lend themselves to global convergence. So here we just have a general log posterior for an arbitrary Bayesian network. We define some terms. So H is a specific hypothesis. So H is a specific instantiation of the hidden variables in the model. E is the set of observed nodes. Theta are some parameters which we'd like to learn. And I should say that we can see in the breakdown, specifically in the negative term where we marginalize over all of the hidden states, we firstly assume that you have a parameter for each hidden state for each hypothesis. Although if you have fewer parameters, if you have fewer data to learn, then parameter estimation becomes strictly easier. And furthermore, we assume that virtual evidence is in play. So the emission densities are possibly unnormalized. Now, in the decomposition of the log posterior, the most complicated term is by far the log likelihood, so the negative term, where we marginalize over all the hidden states. So in our 2018 NURBS paper, we first sought to characterize when the log likelihood was convex. So of course, the log likelihood, which is parameterized by theta, is convex when the Hessian is positive semi-definite. And of course, the Hessian is positive semi-definite when the following inequality holds. So X is just some arbitrary vector in Rn. Now, if you have a lot of paper and a lot of time, then you can actually work out what this inequality looks like in a little bit more depth. So it looks like the following. So it's fairly complicated. We have 3 separate summations. On the right-hand side of the inequality, we can see that we have a summation which considers first-order derivatives, and that entire quantity is squared. On the left-hand side of the inequality, we have a summation which considers second-order partial derivatives as well as squared x's. So in general, this entire inequality is difficult to find classes of functions for which the inequality is satisfied. However, if you apply Cauchy-Schwarz, you can effectively find out that this entire inequality is satisfied when the following equality is true. So this is great news. This is great news, and this is also terrible news. So the great news is that we simply have to solve this equation. So we simply have to find emission densities whose second order derivative times the function is equal to the first order derivative all squared. But the terrible news, of course, is that this is a nonlinear ODE. So there's actually no general guarantee that you can find analytical solutions to these. But again, if you have mounds of paper, and if you're a little lucky, then you can actually show that this specific nonlinear ODE has a unique and closed form solution, which looks like the following. So the class of functions for which this nonlinear ODE is satisfied corresponds to the functions highlighted in red. So we have alpha times e to the beta theta. So alpha and beta are hyperparameters which are determined by initial conditions from the nonlinear ODE, but you can effectively just treat them as arbitrary hyperparameters. So in our NeurIPS 2018 paper, we called this class of functions, which renders the log likelihood convex virtual emissions, or CVEs for short. So some things to note are that this is actually an expanded version of the log sum x function, which is widely known to be convex. So this is great. This is a really nice result. So one caveat, of course, is that we would ideally like to apply maximum likelihood learning. So convexity of the log likelihood is not the greatest thing for maximum likelihood learning. But luckily, you can actually show that under CVEs, the log posterior score, which we have here, is concave, which is perfect. So that means that if we use CVEs within DIDEA, then conditional maximum likelihood learning is actually concave. And this opens the door for extremely efficient parameter estimation. So after deriving this class of functions, we plugged CVEs into DIDEA to streamline its training framework and make it far more efficient. And we expanded it to learn far more parameters. So to summarize this trade-off, we have the old training framework for DIDEA on the left, and we have the new framework contrasted on the right. So the old DIDEA framework would only learn a single parameter, and under the new parameter, we actually learn weight for every single shift variable. The old framework relied on a grid search, which was very costly, and under the new framework, we can just apply gradient descent, which is extremely fast and efficient. And under the old framework, there were no theoretical guarantees. But of course, using CVEs, we have global convergence guarantees. So this is all great. Or I should say, this is all great on paper, but what really matters is how well the model performs once we train the parameters. So let's look at some performance plots. So returning to our earlier worm data set, DIDEA trained using CVEs is plotted in black. And we can see that we get a significant boost in accuracy over all methods, especially the old training framework. And most importantly, when we switch to another data set, this trend of improved performance accuracy continues. So DIDEA trained using CVEs is significantly more accurate across the board. And if you go back to our NeurIPS 2018 paper, we actually had far more data sets than this. We had 8 data sets in total. And just to summarize the performance benefits of concave training using CVEs as your emission functions, we'll just summarize the average performance over all 8 data sets evaluated at a very stringent 1% FDR. So DIDEA trained using CVEs identified 16% more spectra than DRIP, or other DBM, and it identified 17.4% more spectra than the MSGF+. So this was an extremely accurate and efficient scoring algorithm. It's actually, I think, the most accurate scoring algorithm that's in existence to date so far. So where do we go from here? So that's all good news. We saw all of these significant performance boosts using convexity, but it turns out that any scoring algorithm for this particular problem, for for peptide identification has severe limitations, and that's just by nature of the problem. But very interestingly, the computational proteomics community has a very nice way of handling these specific inefficiencies from all scoring algorithms. And that brings us to our next topic. So the deficiency which I'm alluding to has to do with PSM scores from different spectra being very difficult to compare. So essentially these scores are uncalibrated, which means that it's very difficult to say how good a PSM score from one spectrum is compared to a PSM score from another spectra. And this has to do with the extremely noisy nature of these spectra. So when it comes time to do our Fdr analysis, this effectively diminishes overall accuracy. So we're leaving a lot of peptide identifications on the table. So what's typically done to recalibrate these scores is called the Percolator algorithm. This is a semi-supervised learning algorithm which trains a linear SVM to recalibrate these scores. The Percolator algorithm looks like as follows. So we begin with our PSMs as well as features derived using any specific scoring algorithm. We perform Fdr analysis on these PSMs. So we identify, using Fdr analysis, we identify a highly confident set of PSMs, usually using a strict Fdr threshold of say 1%. So these highly confident PSMs are assigned positive labels, and all other PSMs are assigned negative labels. An SVM is then trained, a linear SVM is then trained to distinguish between positive and negatively labeled PSMs. Finally, all PSMs are rescored using the learned decision boundary in the previous step. And this process is repeated. So in practice, Percolator is considered the gold standard, and it works great. So here we have the earlier scoring algorithm, which we discussed, XScore, plotted in black. And we have the output of running XScore through Percolator, plotted in orange. So we can see a significant performance boost. And it works for all scoring algorithms. So this would also be true of DIDEA. We would see a significant performance boost. But what's really interesting about it is that if I had plotted the most accurate scoring algorithm, so if I had plotted just DIDEA trained using CVEs, XScore Percolator would actually be more accurate than it. So Percolator has become a standard routine part of computational proteomics pipelines. So this is, this is great. But you don't get anything for free. So what you trade off for in terms of identification accuracy is runtime. So Percolator in practice is extremely slow. And this has become problematic as proteomics datasets have continued to balloon in the past decade. So the reason why Percolator is so slow has to do with both its iterative nature, so it's usually run for 10 iterations or until convergence, and more importantly, within each iteration, cross-validation is performed to reduce overfitting. So in total, a typical run of Percolator consists of calling 270, consists of calling an SVM solver 270 times. So as data sets grow larger, Percolator will just continue to take longer and longer. In practice, it can take anywhere from hours to several days. So in recent work, I've actually been tackling how to reduce these really expensive runtimes in Percolator. And it's led to some very interesting work. So this brings us into the topic of how to effectively accelerate machine learning methods using high performance compute architectures. So we'll start out with Percolator's current SVM solver, which is called CGLS. And we'll effectively look at how we can speed this up exactly without resorting to any types of approximation or anything like that. So CGLS stands for Conjugate Gradient Line Search. And the resulting highly optimized solver, we're going to call CGLS star. So a lot of these HPC optimizations kind of follow a very similar development lifecycle. So we're going to look at on the x-axis several development steps towards leveraging HPC architectures and making CGLS very fast. So on the y-axis plots the percentage of runtime for the original CGLS solver. And this is for just a small development set, a small use development set. So let's say that you're given an algorithm, and what's the first step towards making it run fast? You might think just make the code go fast, which is true. So the first step in this development process was restructuring and streamlining the code, which saw about a 20% reduction. And then you can take large blocks of code and you can translate them down to low-level linear algebra functions using a library like FLOSS or LaPlace, and we see another appreciable reduction. And then finally, we can use massive parallelization using multi-threading on the CPU. So here, NR stands for the number of threads. And we can see as we increase the number of threads, then we continue to see a nice reduction in CGLS runtime. So that's one approach. It's just to leverage high performance compute architectures to make a given algorithm faster. Another approach is to consider a faster solver itself. So CGLS is somewhat older, and in more recent studies, they've shown that the line search in CGLS can actually be improved upon using trust region Newton methods. So perhaps one of the most popular trust region Newton solvers is Tron, which is used in liblinear and scikit-learn for linear SVM problems. So we effectively took Tron and we ported it to Percolator as a solver, as an SVM solver within it. And the port within Percolator followed similar development steps to CGLS star. So we streamlined the code. We mapped a lot of functions to low-level linear algebra functions, and then we massively parallelized the code for multi-threading. So let's look at how these two highly optimized solvers actually perform for a large-scale data set. So here we have a large-scale data set. This is called the Kim data set. Typically in the literature, it was one of the first data sets to map the human proteome, and it's a pretty huge data set. It's slightly over 23 million PSMs. So Percolator runs at about 14.5 hours effectively to process this entire data set. So plotted here, we have the runtimes for both CGLS star and Tron in blue. The x-axis shows the number of threads utilized, and the y-axis shows the factor of speedup compared to the original CGLS solver. So in red, CGLS star, we see some appreciable speedups. It seems to plateau slightly above 2, especially for a large number of threads, say beyond 32. But the newer and more accurate solver Tron really takes off. So you can see that as we approach 48 threads, you almost get a 6-fold speed up. But this kind of, you can imagine that as data sets continue to get larger, we would still like more speed. So what architecture can we leverage, which is well known in the ML community to be fast, to speed up the Tron algorithm? So these are just some things which we discussed before. So I should mention all these speedups are exact. But GPUs are well known and well regarded in the machine learning community for speeding up algorithms. So when an algorithm is amenable towards GPU optimizations, then it can be extremely fast. So this is well known for, of course, deep learning methods and gradient descent. But this has not been explored for higher order algorithms especially intricate algorithms like Tron. So this was actually a topic which I had explored in my NeurIPS 2020 paper last year. So why is it the case that higher order algorithms like Tron have not been explored for GPU optimizations? And it turns out that they actually resist GPU use. So we showed in our paper that if you just look at the bottleneck operations for Tron, which are all matrix vector multiplies are extremely efficient on the GPU. So if you simply plug in the GPU call within the Tron algorithm, you actually see that the Tron algorithm runs slower than if it had just used a single thread. So it's a crazy phenomenon to witness, but in our NeurIPS 2020 paper, we investigated why this is so. And it turns out that the reason why is that the variables within Tron are sequentially dependent, which turns out to be terrible for GPU computing. So what I mean by sequentially dependent, we'll look at in the following cartoon example of the Tron algorithm. So each line depicted is a line from the algorithm. So let's break these lines up into CPU compute and GPU compute. So ideally, the GPU compute being depicted is indicative of a bottleneck that we'd like to port to the GPU. But we can already see, so in lines 2 and 6 and 7, where we have a lot of blue followed by red, we have large chunks of CPU code followed by dependent GPU code, followed by more dependent CPU code. So this means that as soon as a quantity is computed on the device, it has to be transferred over to the GPU. And as soon as the bottleneck is computed on the GPU, it has to be transferred back over to the GPU. However, this is extremely inefficient for GPU computing. So there is a significant amount of latency transferring data back and forth between the CPU and the GPU. So what can we do? What can we do to effectively relieve these sequential dependencies in the algorithm? In the paper, we outline some general principles which will take any CPU-centric algorithm and convert it into a GPU-optimized algorithm. So we'll briefly go over some of these steps. So we can offload more compute to the GPU. So we can make some of these lines entirely red. But of course, we can't make them all red because memory is very limited on the GPU. And another step that we can do is we can compute dependent quantities as early as possible and transfer them back to the CPU, syncing just before they're needed. So sync is meant to be represented as these triangles. So these sets of operations accomplish several things all at once. So they decouple dependencies of variables from the CPU and the GPU. So now we can see that some variables can effectively live entirely on the device without having to be transferred to the CPU. And that's also true of CPU variables. They can live entirely on the CPU and not have to be transferred back and forth to the GPU. This conceals latency. So we're effectively buffering any data transfer that we need to send from the GPU to the CPU with independent CPU compute. The best example of this would be something like line 7 to line 9. So that transfer from the GPU to the CPU has a layer of CPU code, which effectively conceals the latency of that transfer. The GPU is saturated, so we've offloaded as much compute to the GPU as we can, hopefully, without incurring too many penalties. And this also maximizes CPU and GPU concurrency. So both the GPU is running while the CPU is running as much compute as possible in parallel. So, so we took this set of optimization principles when we added it to Tron within Percolator. If you look at the paper, we also showed that this set of principles applies to algorithms within liblinear, and you can get something like an order of magnitude speedups within the already super fast liblinear. But so now we'll look at how these translate to massive proteomics analysis in Percolator. So returning to our Kim dataset, which consists of over 23 million PSMs. We have in pink the fully GPU optimized Tron algorithm. So we can see that just using a single thread and a Tesla V100, which is a very strong GPU, but still, just using a single thread and a GPU gets over a 7-fold speed up. So you can imagine that as the data increases, you start to run into problems with fitting everything in GPU memory. So we also showed in the paper that you can effectively relieve some GPU memory for a small hit in performance runtime. And that corresponds to this green curve, which is called Tron CPU plus GPU. So you effectively offload some of the GPU compute, which you would have done, onto the CPU. And you can see that it still performs very respectively. So it very quickly saturates at a 6-fold speed up. Now, just to really drive this point home, we evaluated a massive proteomics data set consisting of over 210 million PSMs. So this is one of the largest proteomics data sets evaluated so far in the literature. So this data set itself was too large for the memory requirements of the GPU optimized Tron algorithm, but the mixed architecture approach, where we offload some compute to the CPU, handles it just fine. And we can see that the mixed architecture approach significantly outperforms all the previous multi-threaded approaches. It very quickly saturates at around a 5-fold speed up for this massive scale data set. And I didn't list the statistics here, but I think the naive runtime, or the typical runtime for Percolator for this monster data set is about 4.5 days. And using this mixed architecture approach, you can reduce that to just something like 19 hours. So it's extremely efficient. So that covers that specific topic. So to wrap up, we've seen that graphical models may be used for state-of-the-art protein identification accuracy, peptide identification accuracy. We've seen that convexity, and more specifically CVUs, significantly boost the modeling power of graphical models, while also providing theoretical guarantees for conditional maximum likelihood estimation. And we've looked at parallelization and better algorithms using high-performance compute architectures for post-processing analysis, and particularly how to effectively turn any CPU-centric algorithm into a GPU-optimized algorithm. So before we take questions, I'd like to highlight some future work, which I think is extremely interesting. Not so recent, but in the graphical models literature, it's known that learning the emission densities is actually the most difficult aspect of training a dynamic graphical model. So if you can effectively learn the emission densities, the parameters of the emission functions, then you can simply find the transition probabilities using a quadratic program. So that's a paper from ICML in 2013, if anyone is really interested in that. But a really important line of future work in terms of CVEs is looking at how we can relax the assumptions that were used to derive CVEs that we saw in this work. So we use Cauchy-Schwarz to effectively find the nonlinearity, but can we find families of functions which satisfy that bound without using Cauchy-Schwarz? And furthermore, what do the implications of this line of work say about maximum likelihood learning, since we looked at the conditional maximum likelihood learning regime? And I'll end the talk on the final note that proteomics data sets continue to explode at a quick pace. The 210 million data set that we looked at will quickly become just a mediocre or a modest-sized data set, probably in a year or two. So proteomics really needs speed-ups, and this is not only true because the data sets are exploding, but also because machine learning methods are growing in popularity in the field. So I'll take questions at this point.
Thank you so much, John. So any questions? So I have a question. So this GPU last part that you talked about for Tron. So this can be actually applied to any kind of second order method for machine learning, right?
That's right. Mm-hmm.
That would be really nice. So do you plan to release this?
Yeah, so I've released the source code for the nerds paper. So,
nice.
So it has liblinear, the liblinear Tron optimized algorithm for GPUs, and it has Percolator. And in future work, I'm actually releasing some ultra-fast Percolator-like code.
That would be really nice because then, so this perhaps opens a path for all the second order optimization methods that are super expensive these days to kind of be applied, right?
Yeah,
Minimize the stuff. That's really nice.
And kind of,
Great.
so the thing that we highlighted in the nerds paper was that, so Tron is a specific implementation, say in liblinear. But now that you have a GPU optimized version, you could port it to, say, PyTorch, and you could use AutoGrad and things like that to explore its use for deep learning models.
Yes, that would be really nice. And do you, like, so you mentioned that to kind of address these memory constraints because GPUs have a limited memory, so you can use the combined version with the CPU plus GPU, right? For if you have big models for those AGIs.
Yeah. So one thing that I didn't cover was, so it does become tricky how much you would like to optimize second order algorithm. So it becomes interesting because Tron for logistic regression is nice. It just is, you can just optimize it for GPU use using those principles. But when you look at the Tron SVM algorithm, it actually relies on random access, which in GPU computing is a huge no-no. So you need memory to be laid out linearly on the GPU. So you have this, so that you don't incur too much compute overhead, you have to effectively do this random access on the device. So you have a second buffer, which is of size the original data set. And you do this random access to construct a submatrix on the device so that you don't get penalized.
I see. I see.
But that becomes like a more specific constraint for SVMs.
Good. So any other questions? Feel free to write in the chat if there is any.
You might also see some GPU optimized, some modular optimization.
Yes. Are you working on that?
I don't know how much I can talk about it, but yeah, Rishabh was really enthusiastic about doing some GPU stuff.
I see. So we may get see something soon.
Yeah, I hope so.
Sounds great. That would be interesting.
Yeah, GPU. I think GPUs haven't been explored at length like they could be.
Yeah. Okay, thank you so much. Thank you, everybody. Probably we can stop the recording.